Very good morning. So today let us cover a Kohonen Self Organizing Map. That is, Self Organizing Maps actually comes under the category of the competitive learning networks. Now, Kohonen Self Organizing Map is basically a clustering neural network which works on the principle of winner takes all concept. That is, if suppose there are n number of participating units, then at any iteration, at any point of time, only one of the unit would be declared as a winner. And then we would be updating the weights of the weights corresponding to all the units which are uh, considered as nearby units of that winning neural network neuron. It actually exploits the concept of topological structure among the cluster units. We will be talking about this topological structure afterwards. So let us assume that the output units are organized into one or two dimensional arrays. That is what actually the structure, topological structure means. All the clusters would be organized in either the one dimension or the two dimensional arrays. Now for a given cluster unit, say suppose yi, its neighborhood would be defined in terms of a radius r, which is a set of all the units which comes under within the range of r. This radius r has to be defined separately for each and every problem. Now, some of the examples could be the way this structure R or this organizing map can be defined. The structure can be defined. Over here, we can see that if this is the neuron we are talking about, then we can define a structure in this rectangular structure. So for this neuron, all the neurons which comes in the neighborhood of one area can be declared as the participating or the near neurons. Similarly, we talk about two neighborhood corresponding to the given neuron, then all these neurons in this structure would be in this area would be declared as what the nearby neurons. Another structure could be another arrangement could be this way also. So the arrangements can be different, and that is how we need to define the value of R, which would declare a region in which corresponding neurons neighbors would be declared or defined. Now the overall idea is that the patterns which are close to each other should be mapped to the cluster with a physical proximity. And that physical proximity has to be defined mathematically. Now during the clustering process, the network would organize itself gradually so that the patterns, those that are close to each other, would form a cluster. And we would be updating the weights, or we would be updating only those neurons which falls under the proximity of that vector structure. Very obviously, this learning comes under the category of unsupervised learning, and the weight vectors associated with the cluster units will act as the exemplar for all these patterns belonging to that cluster. We would also call this as a code vector. Now, during the training, the cluster unit whose weight vector is closest to that given input pattern that we are trying to associate with one of the clusters would be declared as the winner. And the weight vector of all those cluster units, the weight vectors of all the cluster units which are close to this winner neuron would be updated, and rest of the weights will not be touched upon. Anyway, this can be a simple structure of a SOM where we have the input layer, right, and we have the corresponding output layer. And here we have declared or assume the number of clusters also. So we have m input units and we have n output units, and correspond to each and every output unit we have considered or we have assumed to be assumed a cluster. So each output unit will represent a cluster, and the cluster units may be arranged in some specific arrangement, which can be one or two dimensional arrays. So let us understand the entire algorithm of SOAM by taking a very simple example, and then we'll come on to discuss the architecture and as well as the algorithm that is working behind it. So suppose we are taking an example, consider four input patterns. So these are four input patterns that we want to cluster. And we want to, suppose I've also assumed that the number of clusters would be two. So ideally, if we talk about the structure, this could be a possible architecture or structure corresponding to this given column. There we have four input patterns and we have two output units, and corresponding to output units, we have two clusters. Right? The weights have been marked in this manner. So the exemplar or the code vector for the cluster C1 and C2 over here in this example can be defined in this way, right? Where the weight W11, weight W21, and weight 31 would correspond to the cluster C1, and similarly the weight 12, W22, and weight W32 would correspond to the cluster C2. Now, as a part of the algorithm, the first part or the step 0, I would call it, comes the initialization part. Now, in the initialization part, we would be doing three different aspects. One is the initialization of the weight matrix. Here we have assumed a random initialization of the weight matrix. I'm solving this same problem corresponding to this given input. So, corresponding to this, we have to initialize the weight of this size. So, this is what we have initialized the weight. And mind you, this is just a random initialization. That is what we do with most of the neural networks. Now, the second part would be in the initialization part is defining the topological neighborhood. Over here, since we have only two cluster units, so we have initialized the radius to be 0 only. So as a matter of fact, it is not going to play any role over here, but we can understand the importance of radius as well. So that's why we have defined the value r. But over here, we are taking the value of r is equal to 0. So, and the third part under the initialization part is setting the learning rate. So again, randomly I have taken learning rate to be 0.8. So we will geometrically decrease it with a factor of 0.5 after every epoch of training. Mind you, what I'm saying is this learning rate in most of the networks, as we have discussed earlier, normally remains constant. But over here, we would be decreasing this learning rate with a factor of 0.5 after every epoch of training, because the concept is we want to ensure that whatever input pattern comes in, it gets clustered as precisely as possible. So we will be decreasing this learning rate in every iteration or after every epoch. We'll come to that later on. Now, the first step of the algorithm is we would be running the entire algorithm while a stopping condition is satisfied. So we need to define what could be the stopping criteria. So while the stopping criteria is not satisfied, we would be executing this algorithm, which comprises of 8 steps. So from step 2 to 8, it would be under continuous loop unless the stopping condition is satisfied. I'm covering the algorithm also along with the exam. So over here, we have made a very simple assumption regarding the stopping criteria. When the weight adjustment becomes less than or equal to 0.01, that is, I can talk about this as in terms of percentage, 1% of error is there, then I could declare this to be the stopping condition or stopping criteria for my algorithm. The net is assumed to have converged, right? So this percentage or this value could be defined by the user. And initially, the stopping condition is definitely false, so therefore we would begin the training, and we would directly jump to the step 2. Now, step 3. Now, for each exemplar or the code vector, let's suppose W asterisk J, we need to find the distance between the input vector, over here it is Si, and the corresponding weight vector or the weight code vector. The concept is, uh, for whatever units or for whatever input pattern, we would find the minimum distance between the input vector and the weight vector, right? So we would be calculating the distance correspond to each and every input vector, and then we would be deciding that for corresponding input vector, which input vector is approximately closest to which of the cluster units or the output units. And for a given pattern, if it is closer to suppose cluster 1, then cluster 1 would be declared as a winner. I'm talking about distance. If in case the distance is smaller for the cluster 2 between the input pattern and the output unit, then the cluster 2 would be declared as a winner. Now, this distance metric can be again defined mathematically in different ways. Over here, we have taken the equivalent distance concept, so which has been defined as the square of the difference between xi and the code vector. Now, in this particular example, say this is our weight vector, right? And this is our input vector. So initially, we would start by taking the first input, that is S1 is equal to 100. So what we need to do is we need to find the distance corresponding to output unit 1 and also corresponding to the output unit 2. So therefore, let us do, we have calculated distance corresponding to the first cluster, that is D1. And using the same formula that we have defined, that is the equivalent distance, we would be finding the equivalent distance between the input vector, this is 100, and the first code vector, that is 0.5, 0.8, and 0.4, right? So what we have done is 1 minus of 0.5, then again 0 minus of 0.8 square, then we have 0 minus of 0.4 whole square, right? So this is how we are going to calculate the distance vector corresponding to the first input vector and the cluster 1, which comes out to be 1.05. In the same manner, we need to find the distance corresponding to the cluster unit 2 with respect to the input vector 1, right? So same way, we have calculated D2, again 1 minus of 0.3 square, again 0 minus of 0.5 whole square, and 0 minus of 0.3 whole square, which comes out to be 0.83. Now when we compare this D1 and D2, definitely the D2 comes to be a smaller value. So this corresponding to this input vector S1, at this point of time, the cluster unit 2 would be declared as a winner, right? Now the next step, which I have called it as a step 4, we need to find the index j so that dj is minimum. So over here, index j would be 2 because corresponding to this, the 0.83 is smaller than 0.105. So d2 is less than d1. So S1 is closer to cluster unit 2. Now we need to adjust the code vector corresponding to W2, right? We need to adjust the code vector corresponding to W2. So the next step would be to update the weights of all the units within the specified neighborhood of J, right? As defined by the value of R. Now for all the J's, such that we have defined the proximity rule, the value of radius. That is, we need to define some mechanism where we can declare what all neurons are nearby to a given winning neuron. So I have to define a rule, right? Since we have just two cluster units, so we have taken R is equal to 0. A very simplified manner could have been this way, where we have defined the closeness as the neighboring neurons by this formula. J minus of R is less than or equal to J, less than or equal to J plus of R. Definitely, since R has been taken 0, so it is not going to make any difference. And we would be definitely, therefore, adjusting the weights corresponding to the winning unit only, because uh, there's no point in declaring again C1 as the neighboring unit, since there are only two neurons, two output units. So, but in case we had more number of output neurons, then this formula could have been uh, would have produced a different kind of result. So for I is equal to 1 to m, this is how this, because we need to define how and in what manner I want to update the weights. So weight updation rule also has to be defined. So very simplified method has been used over here. So the new weight would be updated as the old weight plus this is the learning rate, which we have defined to be 0.8 value, and the difference between your xi, that is the input, and the old corresponding weight or the code vector. Since again यहाँ पे since r is equal to 0, so we need to adjust the weight vector of the winning neuron only, as we have already discussed. So what we need to do is I have to adjust all the weights corresponding to the cluster 2, right? So we would be adjusting 0.3, 0.5, and 0.3 would be updated, whereas 0.5, 0.8, and 0.4 would remain unchanged, right? So that is what this 0.3 corresponds to W12. So W12 new would be W12 old. Old value is 0.3. Learning rate, which is 0.8. Xi, because we are taking the present input, we just process this input 1. So this present input is 100. So 1 minus of old weight. Again, the old weight is 0.3. So which comes out to be 0.86. In similar manner, I have to update this 0.5 also. So in the same manner, the 0.5, this weight would be adjusted as what? W22 old weight, old value plus again the same formula, which would give you 0.1. And similarly, W32, that is 0.3, would also get updated. So by updation of this step, we would get a new weight vector where the first code vector remains unchanged, but the second code vector gets updated as corresponding to the winning neuron, which was corresponding to cluster 2, right? Now, we now proceed to train the second input pattern. See, we have done with the first input pattern, right? So we have to cover the epoch 1. In epoch 1, we would be covering all the input patterns. And then we'll see whether we have reached to the stopping condition or not. Since we are remaining with 3 more patterns. So as of now, the algorithm will not break. So for the second pattern, which is S2 is equal to 0, 0, 1, the same step would continue. Again, we need to come to the step 2. That is for each training vector Si, we would do the steps 3 to 5. In step 3, what we have? For each exemplar vector, again, we need to find the distance dj between. Now the input vector is Si, that is 0, 0, 1, and the weight vector, right? Now, the same manner we did it previously, we would calculate D1, right? So in D1, how it would be calculated? D1 would be corresponding to the input vector, this 0, 1, 1, 0, 0, 1, sorry. We would be finding the difference between 0 and minus of 0.5. We are taking the first exemplar, that is D1. Similarly, 0, the second input, minus of 0.8, and similarly 1 minus of 0.4. So again, we have calculated D1 and D2. So by comparing D1 and D2, definitely this time the D1 comes out to be smaller value as compared to D2, right? So we reach to the step 4 where we have to find index J such that which of D1, D2 is minimum. So over here, J would be 1 because D1 is getting a smaller value, right? Moving to step 5, we have to update the weights of all the units within the neighbors of J, right? So for all the J such that again the same rule has been followed. J minus of R is less than equal to J, less than equal to J plus of R. We need to update the weights, new weights. Now this time all the weights corresponding to the first code vector would get updated, and this weight vector would remain unchanged, right? So we would be getting updated values for 0 0.5, 0 0.8, and 0.4. Let us see how this is the case, right? So, so again, uh, since the winner is G1, 1.25. So currently W is this and X2 is this. So W11, I would W11 over here is zero point 0.5. So zero point 0.5 plus of applying this entire formula corresponding to X2. We have got zero point 0.1 corresponding to W11, right? So zero point 0.5 would be now updated to 0.1. Similarly, 0.12 would be updated to 0.16 and zero point 0.4 would be updated to 0.88. So applying this, the new and the present weight vector after training the uh, second pattern, this is what we have achieved, right? So by applying the same manner, we have to apply for two remaining input vectors, S3 and S4. So let us see how things looks. So we made a table in the initialization part, which I have named as equation 0. We started from here. This was the code vectors for C1 and C2, right? And after S1, we have changed that. We have seen that after giving the input pattern 1, the cluster 2 was the winner. So there was no change in C1. So the change vector or the code vector corresponding to C2 was this. Similarly, after giving the second input pattern, we found that the winner was C1. So no change was done for C2, and the changed C1 was this. After applying the input vector 3 in the same manner, we would find that the cluster C2 is the winner. So definitely there would be no change in C1, and the new values for C2 would be this. And in the same manner, after applying the cluster input unit 4, the cluster C1 would be declared as a winner. No change in the second cluster, and this would be the updated value. So by applying after applying all the four input patterns at the end of the first epoch, that is first epoch means that we have tried all the given input patterns. So this would be the condition after the first epoch, right? Now, definitely, in order to see whether we have achieved the stopping criteria or not, this does not achieve the stopping criteria. So after epoch 2, you need to run or you write a code to understand that it may take a number of epochs. So after epoch 2, this would be the condition. Again, we have not reached the stopping condition because we want each and every value in the weight vector should have should be under the error percentage of just 1% error is required. So so what we have seen after 19 epochs, that is what has been found. The weight vector becomes of this nature, and there is hardly any change from W19 to W because W18 and W19 is almost same set of values. It is resulting in the same set of values. So we can see that, or we can assume that the convergence has reached. So we need to draw a graph. We need to code this in order to understand which W19 as we have calculated may not be the correct. It may result in a local error also, so local optima also. So we have to see after implementation only we can come to know that what is the convergence rate. So this is how the algorithm works. And if you want, uh, this algorithm has been presented in the form of a flow chart also. We did the initialization part where we initialize the weight vector, we initialize the R also. Then we test it for this stopping criteria, and if it achieves, then definitely it's the end of the algorithm. If it is false, then we used to start taking the input patterns. Then we used to determine the distance between the input and the corresponding code vectors, right? Then we used to identify that correspond to which in code vector the minimum value has been achieved. Then we used to update the code vectors corresponding to the winning neuron. And again, if no more training is required, then we can put this to the end. Otherwise, if more training is required, uh, change the learning rate. And say this is the case we haven't covered into the example. So after epoch 1, it could be the case that we can change the learning rate also, because I've already discussed that learning rate would be 0.5 into the learning rate which was previously. So after each and every epoch, we would be also updating the learning rate also, right? And we can also update the value of R, although the value of R in our example had no significance. But ideally, we need to reduce uh, the 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 value of R also. We need to reduce the proximity area so that we are sure that whatever clustering would be done, it would be to some extent would be perfect one. So this is how the entire algorithm works. Thank you for